Recording. Okay, so let's get started with class for the day. So we have a little bit of stuff left over from the previous lecture, and then we'll get started with the next one. It's nice to see everybody. I think there aren't too many announcements. Your homework is out. You should, I'll continue to remind you that you have a project that exists, and you should think about it someday. Other than that, I think we're good to go. And many thanks to Kartik, who apparently poured his heart out to the previous instructor, and the boards were clean. So this is a good day for everybody, and now I'm only a little late. Okay, so we're going to get started by wrapping up the previous lecture and then diving into the next one. I'll try to keep this one short. Well, keep this part short. I'm guessing the whole thing will go long, and then we'll see how far we get. The one kind of remaining piece of our last lecture that we didn't get to was just what data structures do people use for storing triangle meshes. This is a whole topic unto itself. If you take a geometry processing course, you'll find many such options. So I thought I would just very quickly highlight a few so that you can navigate the course homeworks, and there's all kinds of interesting stuff to be done. Probably the simplest one is to just store a list of triangles, just one coordinate after the next, like we see on the screen. There actually are file formats that do exactly this. And actually, for a lot of kind of video game style applications, that's perfectly fine, right? Because if you know in the computer graphics pipeline, like when you're using OpenGL, here I have extremely outdated OpenGL 1.0 call. You literally give your graphics card just a list of triangles, and it renders it one after the next, at least conceptually. And so from perspective of rendering, this is perfectly fine. But one thing that we'll see is that many of the operations we're going to be doing on meshes involve things like, look at all the neighbors of this vertex. And obviously, if I have a data structure like this, then I'm not in very good shape for that setup. Yeah. Moreover, here, notice that like the same vertex is going to appear more than one time, which is not so good. We can at least compress that issue by making a format which is one of the more popular ways to store a triangle mesh called OBJ. You may have encountered files with this extension before if you played with MeshLab. And OBJ is a very simple file format. It's just a list of vertex positions, but now it's like if one vertex is shared among triangles, you only have it once. And then a list of triangles, F, remember, stands for face, thank you, which kind of index into it. So at the very least, if you have the same vertex more than once, it doesn't get repeated, which is a good thing. But still, for example, let's say I wanted to take a triangle mesh and smooth it out. So here's a very simple algorithm for doing that. You could probably kind of guess something like this, where maybe I iterate over every vertex, and for every vertex, I take the average of the vertex and its neighbors, right? So this is like some kind of smoothing operation. Later on, we'll call this Laplacian smoothing in this class, but you could have kind of just intuited that this algorithm does something like that. Would this be particularly easy to implement on a triangle mesh that is stored as an yes, as an OBJ, at least the way that I've written the for loops here? I see some nods and some head shakes. I mean, the answer is sort of halfway in between. There are ways to reshape this algorithm in particular that would make it OK to implement in that data structure. But at least as written, there's this average of neighbors term here. And given a vertex, enumerating its neighbors using that OBJ file format is not so obvious, right? And so there are all kinds of clever data structures out there that are trying to essentially make it easier to carry out certain queries on triangle meshes that are very common. So here's a list. Like maybe I want all of the vertices that are next to a given vertex. Maybe I want all the triangles that are adjacent to an edge, all the edges adjacent to a face, and so on. Notice that there's one word here that is shared in common among all these queries, which is like neighboring or adjacent, right? And essentially, a lot of the data structures that we see for triangle meshes are kind of optimized for like walking around the topology of the mesh. At least when you do this on the CPU, right? On your graphics card, it's a slightly different story, because these kinds of things are hard to parallelize. So there's one data structure in particular which is worth noting. This is called a half-edge data structure, which is one of the more common data structures in geometry processing. At least in principle, I think this is the one we all teach. In practice, oftentimes you can get away without a half-edge, and they're so annoying to implement, I think people try to avoid it. How many of us have encountered a linked list before? Sweet. So a half-edge is basically a linked list on steroids here. And it's got like a linked list with pointers pointing every which way. And setting one of these things up is just a giant headache. And so in particular, a half-edge data structure has sort of objects of three different types. There's vertices, faces, and then this object which is almost edges, but we're going to see, at least for oriented meshes, that rather than having edges, we're going to have an object called a half edge. So the picture to have in mind is if I have two triangles that share an edge, like these, then we can think of there being, let's see, counterclockwise, so probably kind of two half edges, which pictorially we'll think about kind of like the edge on one triangle side on the edge on the other, right? That's the picture to have in mind, okay? So again, a different way to put it is that we can think of a half edge as an oriented edge, right? So edge ij and edge ji are now two separate objects, okay? So a half edge is pointer soup. So we have all these different objects, vertices, faces, edges, and each one of them is like a little struct that contains pointers to other objects, okay? So let me give you an example. The vertex is going to store an arbitrary outgoing half edge. Meaning, so for example, this vertex on the bottom left, maybe it just has a pointer to that half edge. It actually doesn't matter which half edge, we're gonna find out, okay? And we'll assume that all the half edges are oriented consistently, so like they're all counterclockwise, every triangle. With me so far? Cool. All right, every face, oh, the vertices probably also store their position, by the way. I'm just focusing on topology for now. Every face will also contain one half edge. So like, for instance, maybe this triangle contains a pointer to that half edge. You're going to see it's called the half edge data structure because this is going to be the main object that you're using to move around, okay? And now a half edge stores all kinds of stuff. This is why this pointer soup is so annoying to get right. Like writing, you guys whine about your homework, but I didn't have you implement a half edge, and my old course used to, and those are no fun. So like for instance, we're going to have 4 different pointers inside of a half edge. So a half edge will have a flip pointer, which is going to flip to the half edge that points in the other direction. It's going to have a next pointer, which will give you the half edge whose tail is sitting at the head of the previous half edge. So like that would be the next pointer. So it's like rotating around the same triangle, okay? It's going to contain a face pointer, which is just a pointer to whatever triangle it's sitting on. And it's going to contain a vertex pointer, which is going to be a pointer to the vertex specifically at its tail. Okay? So just pointer soup every which way. Does everybody understand all these 4 topological operations here? Cool. So half-edge data structures are really convenient because you can do sneaky things like walk around the one ring of a vertex very easily. So here I've given you pseudocode for one example where I iterate over all the neighbors of a vertex. Okay? So here's how I can do that. And think about it this way. So let's say that I'm sitting at this vertex here, and I want one of its neighbors, right? Well, remember that every vertex has an out half edge pointer. So maybe I do like this guy, right? This guy, I can flip to get that guy. And now I take its base, and I have one of the neighboring vertices. You see what I did there? So vertex, out, flip, next. Okay? And now the question is, how can I kind of loop onto the next neighbor? Well, I can keep walking. Notice if I do a next here, I got to the neighboring vertex. Right? And so if you kind of look at the pseudocode here, that's precisely what it's doing. It's doing this sort of, you know, keep on doing the flip out, you know, rotate around the one ring until you get back where you started. Okay? So we're not going to go into this in a lot of detail because most of our homework assignments will not require this fancy data structure. Like this isn't a course specifically on like mesh editing, but it is just worth being aware that this is sort of the typical thing people do. There's a lot of like little localized topological operations that go on there, and you should all thank your lucky stars that with high probability somebody else implemented them all, and you don't have to deal with that. This is only scratching the surface, by the way. There are all kinds of cool data structures out there. For example, maybe what you really care about is like streaming data. So think about like VR applications where I'm going to send you this huge sequence of meshes one after the next, and maybe they share topology, but the vertices are moving around, or maybe topology is changing in some incremental fashion. In that case, what you care about is bandwidth, right? And maybe you want to look at like what is the best compression ratio I can get for different topological objects. Or maybe you want to allow for meshes that don't just have triangle faces, but also have squares or something like that. All of these things require special consideration. It's an entire community of people that study it. One final thought before we move on to the next lecture. Something we're going to start doing a lot is storing like functions on surfaces, so like a map from a surface to real values. And one identification that we'll make quite a bit is probably on the triangle mesh case to think of functions as being, associated with just one value per vertex. That's somehow the most natural choice here. One could argue one value per face. We'll see that both of those come up later on in this class. But this is one reasonable choice. For example, if you took my undergrad graphics class, you know that maybe to render such a thing, we would interpolate linearly along each triangle face, right? That's what barycentric coordinates are for. So let's say I gave you a function like this, and I asked you to approximate its integral over the surface. Well, this is kind of a reasonable thing to try and do. How might you go about doing that? Yeah?
So this maps a vertex to a real number.
Mm-hmm.
If every vertex was equally weighted, we could just add the values at each vertex, but we can also sort of think about each vertex as having an area based on the triangles that are associated with it. I don't want to spoil the homework question. But
Go for it.
Okay. So
these are the guys that came to class.
all right. If we associate each vertex with 1/3 of the adjacent triangles, then the total area will add up to 1, I believe.
Okay. If the whole surface has area 1, right? Fantastic. All right, everybody. So you're Stephen, yeah? Matthew. A biblical name. I got it close. Everybody give Matthew a round of applause for a much better answer than I was expecting. Yeah, that's absolutely right. So if I want to take the integral of this function, my first inclination might be to just sum up all the values per vertex. But of course, that doesn't account for the area of the triangles, right? Like it might be that there are some really big triangles adjacent to a given vertex. So as Matthew suggested here, maybe we take 1/3 of all the neighboring triangles areas and kind of account for that at a vertex to get a sum, right? So that's like this picture here. There are a bunch of different formulas for precisely how much of every triangle's area should go to each vertex, and we'll kind of look at that later. But like 1/3 is a reasonable thing. Notice that that actually kind of suggests an interesting picture, and I just wanted to draw it for you for now, and then later on when we talk about exterior calculus, we'll see this really important. There's actually 2 meshes hiding behind every triangle mesh. One of them is made out of triangles, and the other is made out of mostly hexagons. And that mesh looks like this. Essentially, I'm going to put a vertex of my blue mesh at the center of every triangle. When I say center here, I mean it kind of conceptually. This is really a topological object. I'm going to put an edge on the blue mesh for every green edge, basically flipped, right? Because it's connecting the vertices that are associated with neighboring triangles. I'm going to think of faces as cycles. Does this picture kind of make sense? Notice there's 2 meshes. There's a blue one and a green one. So essentially, hiding behind every manifold triangle mesh is an object we're going to call a dual mesh, right? The primal dual shows up a lot in this area, which is this other kind of little ghost mesh that kind of somehow is hiding behind a lot of the calculations that we do. So for instance, if we think of this green vertex here as a 0-dimensional object, notice that like Matthew suggested computing areas, but areas are kind of associated with 2-dimensional things. Conveniently, this green vertex is associated with a 2-dimensional blue face that it's sitting in the middle of. In some sense, you can think of the area of the blue face as the area that we're associating with the green vertex. Now this perspective is a little bit of overkill in this particular example, but it's one that's going to come up a lot when we start talking about like derivatives and Laplacians and surfaces. So I just want to like suggest it now as a thing to think about. Here's another picture of exactly the same kind of thing, now on, for some reason, a very smoothed out Stanford bunny. One kind of fun thing to note is that these 2 meshes have their own half-edge data structures, right? I could construct one for each. One thing you might notice is that actually it's perfectly fine to have half-edge on a mesh with like pentagonal faces. That actually, it works out okay. We're going to need an operation that eventually we're going to call star that will flip me from an element to its dual element, right? So for every primal face, there's a dual vertex. For every primal vertex, there's a dual face, and so on. And we're going to see that there are all kinds of interesting relationships come out. If you extend the half-edge data structure to this case, so you add this one additional operation, you get a new data structure called the quad edge, which makes perfect sense because now every edge kind of has 4 copies instead of 2. I believe this is due to my PhD advisor, actually. And And now we introduce a second operation, kind of like that star, which rotates an edge kind of 90 degrees conceptually, right? So notice that if I want flip, that's the same as rotate, rotate. Because I go to the dual and then back to the primal. Okay. In any event, I think we'll stop here. The slides also have some pictures of like why you might want to do these kinds of crazy data structures. So one very typical thing is in mesh simplification, where you're like taking edges and vertices and collapsing them in different ways. And you can think about how to like take this soup of pointers and write pretty compact code for updating it for all these different operations. So I'll let you think about that at home since we're running late. But there's some really interesting things hiding here. Essentially, it's just a lot of bookkeeping. Okay. So I think sort of the takeaway of this quick discussion, which isn't really today's lecture, is that the fancier the data structure you get simpler traversal, but you have a lot more bookkeeping, right? Like just constructing a half edge from an OBJ file is a non-trivial kind of algorithmic task. Like it requires some thinking to get it right. Okay. And finally, I'll note that, of course, there are many other geometric representations. Implicit surfaces are very popular in deep learning right now. In fluid simulation, there's something called smooth particle hydrodynamics, where you represent a volume as sort of a collection of particles, which is sort of cool in practice, but then actually extracting the surface is quite tricky. That's why a lot of fluid surfaces from like low quality fluid simulation kind of look a little bumpy, right? Because there's like little particles they're using. And then in computer-aided design, there's a whole zoo of representations as well. These tend to be higher order polynomial patches like quadrics and so on, which are really important if you care about modeling smooth objects, right? Like I want panels on my car I'm going to actually manufacture. I don't want somebody to get really close to my car and like see mesh edges, right? So actually having like high order patches is important in that community. And they think a lot about like how to join them together with different levels of continuity, right? Kind of like we talked about for curves. And then finally in graphics, subdivision surfaces are quite important, and this is like a methodology of creating smooth objects with many vertices out of coarse objects with not very many. Okay? These are all just Google search terms for you to look at later. They're not the focus in this course. Okay, so I think maybe we'll stop there and we'll move on to the main topic of discussion for today, which is curvature. And this is really the meat of our introduction to differential geometry. I'm going to have to flip, which is going to cause total chaos in OBS.